Good. Oh, I hope you get some people online.
Oh, I'm sure we will.
I'm sure you will. I was thinking,
Doesn't really work me, have we done?
I was just going to join online and I thought, oh, I'll come down because it's first. Welcome to the room. How's things? Oh, good work. Excellent. I've just moved to the Otago Regional Council.
Have you?
Yeah. So I'm
What team?
in the strategy team. I'm doing like climate strategy for the region. So
Cool.
yeah, it is quite exciting.
So who's this at the moment?
We've got a general manager called Amanda.
Yeah.
Yeah. So that would be a team. Yeah. So I'm going to be getting quite involved in that
You'll have
this
to.
afternoon.
Yeah.
Which is just pretty cool. But right now I'm just absorbing.
Yeah.
That's really cool. Yeah. 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 Must be really.
We were up in I was up in Avalon last week, and people mentioned it, but we had a workshop for Pusica fuel kind of things for Kate Clark. They're mainly kind of talking about what we need to do down there to up the understanding for the tsunami hazard, but because of the event the other week.
Yeah, because we don't know a huge amount about Pusica, do we?
Yeah.
Yeah.
And I've been talking a lot with Milford Sound Tourism Limited.
Oh right, when you go to tsunami.
Yeah, so they kind of came to us with a request for a proposal, and we turned it back and said, right, $1.5 million probably to do it properly. And then they went, and then they said, well, what can we do now immediately with what we know? So we did a short talk for them around messaging, and our comms team kind of looked at where people pick up their information from being at home or overseas, deciding, all the decision points and so that's been done, and then there seems to be quite a lot happening atmosphere. I don't understand between them and God. Well, I think it's happening. I think something's happening. Still something. I haven't told me it's all week those lunch.
Well, the cool thing about that is that it's going to generate research or research funding.
Yeah.
Maybe. Actually, I just thought quick on this connection. In fact, we see that in the last meeting. And I was wondering about the guests. So you see, no, but we got some colleagues to go and take some under. Did you see it?
Yeah,
amazing.
Yeah, it was
So cool, wasn't it? I just didn't.
When we were there, we didn't have a boat, but because we were there for a snow. Now I've got Jen's little inflatable. Just for them to fly into it.
Yeah, perfect. Take it into someone.
With the same cast of characters.
Good afternoon. And I'm sure many of you here know Simon's for quite some time and know his work quite well. But just in case I miss out any of this important contribution, I have a sheet note here to read it out so that I don't miss any important information. Yeah, so Simon is a principal scientist at GNS Science in Dunedin. His wide-reaching research has played a transformative role in advancing geological knowledge of the South Island, Southern Alps, and Antarctica, and work on Punamu and Haute mineral treasures, has directly supported Iwi Maori, and is part of a broader package of pure and applied work characterizing landscape evolutions and hazards from groundwater, earthquake, landslide, and erosion. The impact of Simon works reach out And Richard has been recognized throughout the multiple national prizes and a Lifetime Achievement Award. And he continues to help communities develop resilience to effects of natural hazards and climate change. And I think the floor is yours, Simon.
Thank you very much. Come here. I don't know if we got people online as well. Oh, online. Oh, yeah, there's people online. Right, great. Thanks for coming. I'm going to assume nothing that and try and work from a base level that people don't know anything about groundwater and don't know anything about Dunedin, and I'll try and build it up. And I thought what I'd do to do that is just sort of go back to a wee bit of groundwater 101. But I'm going to assume that anyone listening does know that there's a problem in South Dunedin. And of course, it's been coming out in the newspaper, and this whole thing kind of really sparked off back in about 2015 with the floods. And we've only really experienced 2 events of flooding since then, but we've been kind of lucky. But now we're really on a pathway to use Dunedin, not only to support Dunedin, but to support actual policy development and things. And one of the key things about South Dunedin and Dunedin as a whole is that there's a real Goldilocks sort of size. We're not too big and we're not too small for a whole lot of really cool things to be happening around trying to understand what do we do about sea level rise and groundwater in New Zealand, not just in Dunedin, but also internationally. So it's a perfect size to have quite a lot of clever researchers in the university and quite a lot of people at the council and people in the city council and the regional council and so forth. And so it's been a real pleasure to work in this space and try and get these lessons sort of out of it and bring them kind of forefront around the world, which is what we've sort of been doing lately. If you don't know, groundwater and rising groundwater causes problems. And the reason is that there's a water table. Here is being the position where you go from unsaturated or semi-saturated to saturated. And as that height of the water goes up, it has an impact on the amount of water that'll come out of the ground, the amount of ponding that will occur in low places, and also the runoff. So the amount that you can infiltrate, as that goes up, the volume of the area that can be stored by rainfall decreases. So as sea level rises, or there's big tides, or there's extreme sea levels, we have this changing storage potential for rainfall, which means that then you have to rely on stormwater systems and so forth to take that water away. You can also change the environment because the groundwater that's pushed by sea level can become saline and change its chemistry. So that's what it's all about, really, is that sea level rise is going to cause all sorts of problems with groundwater coming up, both in terms of the wetness and the springs that you have, the amount of ponding that you have, but also the changing runoff ratio and the amount that you rely on your stormwater networks. One of the problems is, from the point of view of assessing risk, is that there's a whole range of different things that happen, and they're not necessarily going to cause any direct loss of life. Creeping groundwater rising is not really a direct cause of immediate loss of life the way that a flood hazard would be at high velocities. So we get all these different things happening, rising damp in houses, leakage into the stormwater system, into the sewage system. All these things happen well before you actually ever see groundwater. And groundwater is kind of a funny thing because it's hard to see it. So it's actually hard for people to conceptualize it and understand it. And that's what my mission is today, is to help you conceptualize it. And of course, these thresholds all occur at different heights and elevations. So, you could take, for example, buildings, and this is showing you the depth of ground, below ground of the water table. And I've drawn here where it would emerge. But, down at maybe 9 or 10 metres, that's where you start to intersect where the foundations are, and you might change the strength of the ground. Then it might start to seep into basements as it gets a bit shallower to deep basements. Progressively, it starts to affect the foundations and then may start to enter buildings, and once it becomes emergent, start to cause problems in buildings. But it also happens, it impacts on infrastructure, starts to affect the strength of the substrate in the roads. And it can start to affect health. If you're living on very damp ground, you get health issues associated with it. If you start to get ponding, you can get mosquitoes which can transport diseases. So there's a whole range of things where groundwater itself can cause an indirect hazard as well as a direct one. And they can be permanent, where it comes to a level where it's always there and always causing a problem. But on the way, the thing is that groundwater fluctuates all the time, goes up and down, and so you get this episodic effect of the high groundwater that might occur once a year or once a week or maybe once every 10 years. So it's kind of a tricky thing. Now, the best way that I can describe and get your head around what's happening in Dunedin is to ask you to think of it as think of Dunedin a bit like a paper cup, and that the flat area of South Dunedin is just like a leaky paper cup. And it's got some sediment sitting in it. That flat has got the sediment there, but it's also full of water up to a certain level in the pore space, which is shown here with the blue. And it's saturated down below that water table, and above it, it's dry. And the remaining storage is just what can you put in between those grains of sand above the water table. Of course, when it rains, you get some flow across the land from the hills, and that's a real problem in South Dunedin. And you also get rain directly onto there. And so the amount that you can hold will depend on that catchment and so forth. And we've got a system, a human system built across it with engineering. So we've got wastewater pipes that are taking away the sewers. Some of those are clay butted pipes that were made 100 years ago, and they're leaky, so they're acting as drains. Then we've got the stormwater system on top, and we could potentially do some pumping if we wanted to by popping in another straw and giving it a suck. But it may not necessarily work. Now, the thing we've got the problem of in South Dunedin is that we've got water that's coming down on the hills and is hitting at the back of the whole thing, and the groundwater system and the water are trying to get to the lowland and get to the sea, but we have constructed a area of high ground along Portsmouth Drive in Dunedin, which is stopping that water from naturally flowing out. It removes all of the natural outflow, and we're collecting it instead and taking it out via the Portobello Road pumping system. And the water's coming down and it's going across in a sort of a wave, essentially, at a rate that's basically too high, so it floods every now and again. And it's kind of like flattening the curve of arrival at the hospital with COVID. What we want to do is to decrease the numbers of people that are coming into the hospital in COVID and get it to a rate at which we can deal with it. And it's the same with groundwater. You're trying to attenuate that, or with flooding, we're trying to attenuate that wave as it goes across the city, and the amount of groundwater that's there is quite critical in it. So that's the situation we're trying to deal with, but then we've got sea level rise coming on, and you can imagine taking that leaky cup and pushing it down into a bucket. So the permeability of that leakiness is all important. If it's really permeable, the water's just going to come rushing in, and there's not much you can do to suck it away. In fact, if you want to pump it and you want to suck on that straw, you've got to suck the entire bucket dry, i.e. the entire Pacific Ocean, in order to get rid of it. While you're doing that, you're pumping it back into the Pacific Ocean. It ain't going to work. But the advantage is that the ground is actually slower and it's relatively impermeable. So the geology is really critical in terms of what you can do and how you behave. It's quite difficult to quantify the amounts of hill slope runoff, and it's quite difficult to quantify the effects of the human infrastructure. But the other one is quantifying that subsurface behaviour and the position of the groundwater so that you can understand how much you can suck and what the permeability is and what the nature of the storage is underneath. Yeah. So that's the simplistic system. Add to it, there's this other thing, was there's that paper cup ain't just a paper cup that you can deal with physically. It's got all these emotional attachments to it and a whole lot of social responses and things that people want to cling to, which if you didn't have would make Dunedin no fun at all, but having it actually causes a problem. And people have to have, they all have a whole lot of different sort of things, different drivers and thresholds which make them go away. And the classic example being the tent. Here we are, gone camping, it's pouring with rain, and Dad's sitting there going, you'll bloody well enjoy yourselves on your holiday. We're not going yet. While the kids are going, when can we go home? Which is kind of what's going on in a dynamic way in South Dunedin. Now, I'm not going to deal with the social stuff today, not really at all. That's all a whole nother kettle of fish. I'll talk about it briefly at the end, but I want to acknowledge it because it's the most important part. It's way more important than the physical things that are going on. Getting the social stuff right is critical, okay? Right, so let's do one more thing about the geology before I run out of time. And I want to get across two bits of really important things for you to understand, and that's the hydraulic conductivity, or the permeability of the ground, and the storativity. And I'm going to show you that through a couple of kind of experiments made by video with my little wee digger and my little glass boxes, and I've filled them there with some sand on the left and some gravel on the right. And in this case, I've put a litre of water in those fish tanks or pots. And interestingly, see where the saturation is. I've made the water blue, but for the same litre of water, because the porosity is different between gravel and sand, the level of the groundwater is different. And it's higher here in the sand, and the sand also gets a capillary zone above it where it's semi-saturated, quite different from in the gravel where it's lower. Now, what I'm going to do is rain on top of it and see what happens to the water table. And of course, the gravel is highly pervious. It goes through really quickly. It's got high porosity, which is essentially the storativity of the ground, whereas the sand has moderate porosity and moderate storativity. And I'm going to make it rain with a certain amount of litre of water by basically holding a leaky milk jug over the top, and we'll watch what happens. So if I can, let's see, how do I do this? It should come up with an automatic, because I'm on this thing here, maybe that's the problem. Let's see. Yeah, there we go. I think that's going. Yeah. So it's underway. So it's raining now on the top, and you can see the water infiltrate down through the gravel quite quickly. Goes all the way rapidly down to the water table, and the water table rises in the gravel. And you can see it climbing up. And the top's reasonably okay because it infiltrates really quickly. Now we're onto the sand, and it does some weird things. Firstly, it's not making it quickly because it's less permeable, and it ponds, and in fact, the whole sand stack collapses, and you get settlement. And then eventually it climbs its way up. Okay. So I've got sitting in the bottom of this a transducer, which is measuring the pressure change. Now, one of these loggers here, this thing up here, measuring the pressure during that experiment. And I've set the zero time for when it started raining for the storm. And what you see in the red line is that the sand rate, the pressure in that logger goes way up, and the connectedness of the water table, it rises really quickly because there's less storativity there. And it's quite different. It doesn't rise nearly as much in the gravel. And there was a wee break in the thing, and then I had it rain again. I think I must have run out of water or something like that. But the key thing there is the geology is really important for what the groundwater does and what the levels of the water table are in those experiments for what is essentially the same simple little experiment. Now we can just have another look at it. And what I've done is I've put some impervious clay kind of rock crushed stuff on top of the gravel on the right-hand side. So I've got clay and gravel. And on the left, I've got potting mix. So a sort of a biological kind of thing, and the sand underneath. And if you run that experiment, and I think if I'm lucky, it'll go. Maybe down there, maybe another hit. Let's try that. No, yeah. So there's the rain going down on top of it. And you see there's quite a lot of ponding going on at the surface. And it's got wet, and now we're doing it onto the dust, and it's quite different. It won't get through that impervious clay, so we get a separation of the water table. In fact, we get a perched layer, and it takes a very long time for that water to come in and actually start to contribute to the groundwater. And eventually it bursts through, and you end up basically having to, it connects through, slowly kind of goes down, and then bursts through, I think somewhere there, we're nearly there, and makes it rise. And you see a cloudy change in the colour and things like that. So very different depending on the geology. And that's really important for differences in the coastal environment, because an estuarine quiet backwater that has turned into a sediment is often full of clay and woody material and fine grain stuff sitting on top of maybe where the river was before. And it's quite different from the sand that you might have in a sand dune with something on it. And the storativity is different, and the behaviour of the groundwater is very different. And now you can see that that's flowed through and connected. So in that case, we had a very different response to that storm and that pattern in terms of rainfall time. And the soil and the sand on the left and the red had a climb, and then it slowly decreased away. I think actually the potting mix was absorbing some of the water, as opposed to the clay and the gravel, which sort of spiked, and it was feeling some of the effect of the weight of it early on, but it was actually disconnected. And then eventually it started to break through, and you got these kind of spiky kind of behaviours as it broke through and flowed, and then you connected the two up. Okay, so that was a long-winded way to try and get you thinking about the importance of geology and sea level rise. And if we talked about a paper cup and it was leaky, you imagine the differences between, say, having something that's completely impermeable, maybe a glass container that you put in the water, where the sea level rise is never going to get in there and influence that water pressure, versus a situation where maybe it was in a box, a leaky cardboard box or a leaky paper cup, and eventually it starts to get through, and you have this sort of slow impact kind of thing. So conceptually, that's all you need to kind of know about what might be going on. And in South Dunedin, the way that we got in there was to try and understand it, was to take a whole series of pressure transducers and measure what was going on across a network. So the key thing from a survey point of view is that those transducers, you drop them down into a pipe. You drill a hole in the ground, put a pipe in there with slots in it. You hang those transducers in the pipe, and they measure the pressure, which is both air pressure and water pressure above the transducer. Air pressure changes all the day, so you have to measure another place with a pressure transducer at a base station. You subtract off the air pressure, and then you're getting the changing head of water above the transducer. But you also need to know what the level of the water is. so we have to get a GPS. And so you come quietly knocking on the survey department's door and say, here's some chocolate biscuits or a beer. Can I borrow the GPS for a while? And you measure the top of your borehole and you get a really precise measurement. And then you measure downwards with your tape measure to the water level. So we have an electronic tape measure that we pop down in the hole and it goes beep when you hit it, and you can measure it to within a millimetre. And then you get the precise elevation of the water at that time relative to the pressure that you're measuring in that transducer. So you're kind of doing that in 35 different sites all over Dunedin. And what that gives you then is a map of sites that then you can interpolate to give you the water table at a particular time or an average over a particular period. So this is the median of the groundwater shown as a map, coloured oranges for high, blue down at sea level, and contours here. And it shows you then that's the median over the survey period that we had from a whole lot of 15-minute data that's interpolated. And essentially it's telling you that the water flows from its higher above sea level. It's about here, we've got the height here, 1.5 to 2 meters up here, and going downwards towards the sea, and there's a flat area with some bumps and highs, bit of a knob there, but it's sitting above sea level. That's the really critical thing. It's flowing down and out, but it's got shape to it. And then what you want to do is to subtract that elevation in meters New Zealand vertical datum from the LiDAR elevation to get depth to groundwater. So there's a measure of depth to groundwater across Dunedin, which is reflecting that that contour. So the contours on this map are showing you the elevation of groundwater, in vertical datum, New Zealand vertical datum, and then the colour is representing the depth to that relative to the ground surface. And of course, there's a lot more depth down underneath the dunes because the dunes are high and the groundwater is relatively flat. But there's a slope that comes down. And then a lot of South Dunedin, the depth there is, it's around about 0.5 metre to 1 metre below surface. So it's really important for groundwater studies that we can survey accurately enough the height of our measuring points. So, the surveying and having Pascal help me measure things has been really critical in terms of getting the levels right. Because when we're talking about 1 metre of sea level rise, we've got to know the ground elevation to within, 20 centimetres or 10 centimetres. And we need to know the water elevation. But importantly, the water doesn't actually stay static. It moves all the time. So you can then turn that and take your measurements and make it into a movie. So this is a movie now of the Dunedin area. You're going to see there's triangles where our measurement points are. And this is the general outline that you can see in the aerial photo here. So the harbour's up in this area, St Clair, St Kilda down here, the Pacific Ocean and the hills over on the left. And we're going to look at a period back in 2020 when Elton John played at the covered stadium. Do you remember anyone go to that concert? It was down. And everyone got really wet. But once they got there, they were happy because there was a roof over the stadium, unlike other places. So there were these different rainfall. It started off with one rain event, and then there was some more rain, and then the night of the Elton John concert, it really went crazy. And this is the trace here of one of our groundwater boreholes showing you the step up and then the retreat and then the real climb and at Anderson's Bay Road. At one of the other ones at Kennedy Street, it's got a tidal signal. So the ocean was going up and down with the tides in red, and Kennedy Street goes up and down with the tides in a much smaller way. It just gets a fraction of the tides. And then Kennedy Street, the blue, during the event, it climbed up a little bit and decayed away, but it's beating away at a completely different dance. So here we go. We're going to show a movie, if I can get it to go.
I think if I click it, it should start. No, where are we? Let's see what happens if I. Oh, yeah. So there we go. So we're showing in kind of in frames of about what is it? What did I have? 1.5 hours per frame. The colours represent essentially the height of the groundwater, and it's sitting pretty low to start with. And with some of the boreholes, there's one down by the harbour, which is quite tidal. It goes up and down all the time. And Kennedy Street, the one that was beating away, is over here, down by the red here. You can see it going up and down all the time. But generally, they're really sluggish. And then all of a sudden, as it starts to rain, they pick up and you lose all your blue colours. And then that second rain, which is the evening of the Elton John concert on the 4th of February, all of a sudden it just goes haywire. It goes out into yellows and things and then finally into reds. It's really high all the time. Meanwhile, Kennedy Street's still beating away, going up and down because it's highly permeable. Whereas the other ones are less permeable, and we perched this thing right out on the ground. So, conceptually, no one sees groundwater, but you can put it together with the surveying and with the measurement to actually give people a view of this beast that lives underneath South Dunedin and was actually controlling where we're going in the future, which is kind of what it is. It's kind of cool. Okay, so that's what it looks like. And we get this from all these different sites. So here's an example of it. And what we find is that the ups and the downs during the year at Bathgate Park are really reflecting the last 30 days mean rain. The last 30 days of rainfall is approximately what we have in most of South Dunedin. At some sites, it's got that same sort of 30 days of rain beat, but it's got a noisier, kind of a flashy response on top of it because it has essentially a quick flow, like a stream type variation on top. But the modes underneath of the last 30-day average are still present in a lot of them. And you'll see them. Here's a whole lot of examples. There's a couple there with that same mode. And if you've got a really tidal bore, it'll be really blue up and down like that. So there's, I think, Kennedy Street, and there's one other there. The key thing from this work that will save and give Dunedin options is that it's not all smeary blue. It's not all tidal. That it's relatively impermeable and it's responding to rain, not responding to the sea. Go back to that leaky paper cup and remember the straw. If you had to suck it and it was really permeable, you'd have to suck the entire bucket dry. Well, this is saying that only 2 sites here in Dunedin have got that really quick tidal response. Most of it's not. And that's really important for adapting and whether you've got to fight or flight, and whether you can fight or flight, and whether you've got any options at all for engineering. So we now want to know what the groundwater looks like. We've got to develop some models. There's lots of different types of models that you can do with groundwater. You can do analytical solutions, which say, where would the water table be? And if sea level rises by this much, what will the push of the difference between the saline water, which is more dense, and the fresh water, which is less dense, how will that have an effect? You can do numerical models where you actually do the whole flow equation, and you do the groundwater equation where you go from one cell to the next and you measure the whole flow. But they are computationally quite tricky and they take a lot of setup, and you can only do an area like South Dunedin. You can't really do all of the country. So what people tend to do are geospatial models, and that's the thing that I'm going to talk about from here onwards is a geospatial model. We do have other models for South Dunedin, but I'm going to focus on different geospatial models, which is kind of what I've been talking about right up till now anyway, but I just want to hammer it home. So we've got 2 main pieces of work that have just recently come out. There's one that locally got sort of publicity about February 2024 when it was accepted by the Otago Regional Council, and it now drives their hazard portal and the information you would find if you're wanting to find out about groundwater underneath your property. But we've just published this paper also in Earth's Future, which is how do you do it? What's the lesson from Dunedin and how you do this? And it's around it's called empirical models of shallow groundwater. So it's empirical in that we're using observations from those transducers to constrain the uncertainty. And the really important part is that because you're down at the meter scale, you really need to know those variations and that variability if you're going to actually really do something in terms of mitigating it. It's one thing to say, you know, it's approximately here or approximately there. It's another one to start to actually develop mitigation solutions. So this has just sort of recently come out, and we had an article in EOS, flooding from below. It's kind of gone around the world and it's kind of gone slightly viral, and I'm really thrilled with that. And this is a really good time to remind myself to acknowledge there's a lot of people who have been involved in this work one way or another, right from Pascal helping me and lending me, and from the surveying department lending me equipment, which is partly why I'm paying you back with a talk on it, right through to our Marsden project that Tony leads, University of Otago in general, Otago Regional Council and Dunedin City Council and South Dunedin Community Network have been involved. And then we've had collaboration and data sharing from NIWA and from the Natural Hazards Commission, or in those days EQC, helped fund putting the network in. So yeah, lots of people there to thank. So geospatial models. You all probably have done this before. You've got a DEM and you've set it so that anything below a certain elevation goes blue. And you go, you're all doomed in this area. And you couldn't be further wrong. Because what that is it's saying that it's a bathtub model, and it's saying that the water table is flat and you're lifting it by a certain amount, by a meter, and then saying this is where it will be in the future. Or you're saying that the inundation will be from here, will go over a certain amount, or will go up to the edge on the coast a certain amount. And that's saying that the hazard is directly proportional to elevation. And you might be able to get away with doing a national screening for that to say that, yeah, there's a lot of vulnerability in Dunedin, which is essentially what happened in the 2015 Preparing for Rising Seas report. It's kind of useful for that, but that's it. It stops there, because groundwater actually has a slope to it, as I've shown you, and it has a variability to it. In the natural system, it's higher than sea level. And it varies depending on whether it's in sandy sediment or muddy sediment. And it'll go up depending on sea level. It'll depend on the tidal efficiency and the permeability of the ground. It won't necessarily go up linearly. So you've got this natural system, which is more complex. And then on top of that, in a place like Dunedin, we've got an urban system built on top that takes the water away, or that more it goes up, the more head drives in, and the leaky sewers take more groundwater away. And it starts to then affect the efficiency of the sewage system and the wastewater plant at Tahuna. So it's quite different. These empirical models that you can build where you're using a transducer and you're actually getting the shape of the water table are a very different type of geospatial model, much better for actually understanding where the hazard is. And that depth to groundwater that you get from that shape is very, very different than the depth to groundwater that you get from a bathtub model. So if you see bathtub models, and if you're tempted to do it, please do not look at any sort of scale that's sort of less than looking at the entire South Island. Do not use them individually for a city. Use them only to say maybe Christchurch and Dunedin have got different risk profiles. So what we're trying to do is we've got a system here where the water table has variation in elevation down here. We've got all these surveyed measurements of sea level, mean high water springs, high tide, storm surge, extreme sea level, wave setup, and so forth. And then we're trying to understand the depth to groundwater, and we're trying to understand what the storage is in there and how much sort of the transient flooding effect might be compared with other things, with the wave overtopping versus this coming up and driving it and becoming something like that. And the variability of that water table is all important. It really is important in terms of what's going to be exposed to the hazard and how often it's going to be exposed to the hazard. And that's what the empirical models can do. And so what we can measure is, for example, what is the tidal efficiency of the ground? How much does the water table change for every metre of change or for every tide swing in the ocean or the sea? And that's a map of that there that's taken from that monitoring data in the transducers. And we can take that and we can add on that tidal response to, say, the median value, and we can add it on and say that's what it looks like at mean high water springs as an average. But we can do the same. We can say, well, if that does that to mean high water springs, it must, and we've observed that currently, we can say, all right, what is that going to do with the metre of sea level rise? And so we can use that tidal efficiency and that difference in head as you come away from the coast to say, what's it going to look like under different conditions of sea level rise? And that's what we've done. Another thing that's really good to measure is the amount of rise of the water table for every millimetre of rain, which is the rainfall recharge efficiency, essentially, or the rainfall recharge index. And that's a map of that in South Dunedin. So you saw those experiments. Is how much, when you pour a litre of water on or a millimetre of rain, how much will it go up? And what you find is that generally the water table will rise about 7 times in red there, but somewhere between 4 and 7 times more than the millimetres of rain, because that's related to the pore space in the geology. And it's different in a gravel in Christchurch than it is in Dunedin in a kind of a muddy, clayey sediment that's come off volcanic rocks. So we can measure that, and then we can start to look at how much loss of storage will we get in terms of rainfall going in as that water table rises. So now these colours here represent different rainfall amounts in terms of storm return periods of 2-year, 5-year, 10-year and 100-year storm intensities, and where we've got no storage left whatsoever because it will fill that up. And that's currently sitting at sea level rise 0. I've got a 0, 0, 0 there. And now I'm going to show you a movie of what happens, if I'm lucky. Yeah, so this is now changing. 10 centimetres, 20 centimetres, 30 centimetres, 40 centimetres. As that water table comes up, it means that ultimately a 2-year flood event, a 2-year rainfall event, no longer has room to be stored in the ground, which means ultimately the stormwater system has to cope with it all. So you can work out what stormwater needs, but by the time you get to a metre of sea level rise, you will always have all the water going into the stormwater system. So you have to then engineer for that. To show you the effect of that in terms of land, you can plot for the amount of sea level rise here in centimetres. This is the percentage of coastal plain, the percentage of that map in the GIS that is gone and changed colour, that shows you no more storage. And you get quite a different amount if you look at median levels than at mean high water springs or at the 95th percentile. In fact, because of the variability of groundwater, the 95th percentile, in this case here, is currently at about the equivalent of 20 centimetres of sea level rise, higher, and the rate is lower. I think that's how I'm saying it. So essentially, because the 95th percentile is much higher, you have it makes that much difference in sea level rise. And that then means that you can't just go in there and use median values. You've got to be thinking about the extremes, because it's actually quite a big difference in terms of the time shift. It could make a difference of about 50 years. So these curves show you then how that varies over time. Now, quickly I'll do the same thing for groundwater inundation. Let's see if I can get that to work. Yeah, so here 10 centimetres. So this is now the emergence of the groundwater coming out of the ground and where it will emerge. Of course, it's following behind the absorption of the thing, and ultimately the groundwater will come out as sea level gets up to 100 centimetres. So you will get flooding from below, and it'll be permanent flooding all the time. But on the way to becoming permanent flooding, you will be having flooding at high tide, and you'll be having flooding at some extreme sea level. Finally, I can show you the coastal inundation curve, and over time, speaking of which, how much have I got? Yeah. So this now is showing you at 20 centimetres, 30 centimetres, 40 centimetres. So the sea level's coming up and it starts to inundate over Portsmouth Drive. And then it flows in over that small, low bit of land at about 1.82 metres and connects across South Dunedin. The dunes, as long as they don't erode and as long as we can maintain them down here, they are a protective barrier. And the flow rate through to groundwater is relatively slow, but that will precede it getting over the top of the dunes. So in terms of that as a sort of general trend and the effect of groundwater, you can see all of those movies that I just showed you. Here's the loss of storage and the evolution of that colour. You can see it from the back of the room, how it goes red earlier than it goes dark blue, and it goes dark blue earlier than it goes light blue. So that the effect of it is that the loss of storage causes a problem well before the rise of the groundwater, which causes a problem well before we get inundation from the sea. And we can these are set on increments of sea level rise, but you can say roughly what the different time periods would be depending on which RCP scenario or SSP scenario we follow in terms of our CO2 concentrations. So it's not necessarily as bad as what we initially feared, and now we start to think about how does that profile look? So we're going to have this contribution to pluvial flooding from groundwater. It's going to exacerbate the present pluvial flood risk for quite some time, well before we start to see it emerge just on these high tide events or extreme sea level or storm surge events. And then eventually some parts will start to get wet. And then later we get a completely different curve. It's a different shape. That inundation from the sea is dependent on the topography and the shape of the land, whereas the groundwater flow is dependent on the permeability of the land, and the curve for the contribution is dependent on that storativity that we talked about right at the start. So three different things that are quite different in different places, but they come out here in Dunedin in terms of how it plays out. And it's really hard because the time frame we've got one hazard to deal with perhaps for the first 30 centimetres of sea level rise, and then we've got another hazard to deal with, and then we've got another one. And if we want to get rid of the pluvial related flooding, we've got to build stormwater drains that take away the rainfall. If we want to get rid of groundwater problems, we've got to have field drains that take away the groundwater or pumping. And then coastal inundation, we need a completely different set of engineering things. So there's a spectrum of them there. But the problem is that 30 centimetres of sea level rise could be as little as 30 years. It's probably 50 years. So if you're trying to spend, I don't know, $100 million on infrastructure, you've got to get that return and know what's happening next in order to actually justify that investment. And that's a really tricky time frame. If it was 100 years, it'd be fine. But when it steps down to 30, 50 years, that's really hard. So it becomes hard. But the other thing is that most of our planning is tending to be done on median levels, on general state of where you get to, on the permanent condition. And what I've shown you here is it's the episodic ones. It's the size of the rainfall and the return of the rainfall that is important. It's the height of the tide and the height of the groundwater that actually drives the hazard. And that means that we need to get on top of the episodic processes and the antecedent, the pre-episode conditions, rather than looking at mean state. And the problem with to my mind, with the way that we're currently going, is we tend to look at what's the mean model going to look like way out at 2050, 2080, 2100, as opposed to how we're getting there through the episodic kind of state. So there's a whole lot of uncertainties and caveats that go with this in this report. The geometric models that I've got and I've presented are a worst case scenario. It may be better than that, but you're much better to plan on a worst case scenario and get it wrong than to go with and have a conservative approach than to have it the other way around. So yeah, lots of caveats. The report is fed into the South Dunedin Future program. It's around what is happening. Now they've taken it the next step, and they've got both risk analysis, what's at risk to it, and then some adaptation solutions that they're discussing with the community at the moment around where do we go. And so it's at the stage where what they've done is they've costed out what it costs to do nothing and stay with status quo. Then they've looked at the other options and they said, how much will this option cost? But what's the residual risk? What if it doesn't work and we overtop it, or it gets right, we get it wrong, what will the other cost be? So there's two numbers that are really important to juggle. That actual, what are we protecting, but what is the residual risk? And so that's why these diagrams that you can get off the Dunedin City Council website had those two numbers. It's very clear that the current status quo is not an option because it's probably the most expensive option, both in residual risk and in cost from loss from insurance. People are now kind of trying to digest that, and we're trying to get the concept of what do they want. Of course, everyone's going to want Rolls Royce. It's how do we fund it? And that really comes down to, can we actually develop things with central government? Do we have to do it all locally? Or to what extent will the finance sector come and play games? So, there's a lot of banks and products overseas now that are looking at reverse mortgages or equivalent of reverse mortgages, but basically that you can work your way out of ownership of a property and into another one. And so there's products being developed there. They're not really there yet in New Zealand, but they may well come in the future. I've got a couple. I might just take another quick minute to just reinforce that condition thing and tell you a tiny bit about our Marsden. But to go back to, here's a groundwater measurement down at Tahuna Road, and in July 2022 we had one of our biggest rainstorm, or it was our wettest month for July. We had two big kind of continual wet yuck periods, but they weren't enough to seriously flood the ground. But here the water was going up and down a bit, and then we got the first bit of rain and the second bit of rain, and then this really big event. And that's kind of like that movie that you saw at the Elton John event. But then it died down for a bit, and luckily the water recessed. But then we had another one, and it jumped back up, and it got right up to ground level, as shown by that green line. Now, imagine if we didn't have that full week or so of recession, and that we had put this event here on top of that little rain event there, and it jumped to here. It would have been a different scenario for South Dunedin than we had. Luckily, it just held in there. It was right on the cusp. But we had an event last year where obviously we had the floods. So through our Marsden project, we've been exploring this hypothesis that we have around the frequency of events. The groundwater is continually rising, shown by the dark blue colour. And as it does this, the rainfall events on top of them are adding to it and nearly getting to ground level. And ground level shown with a dashed line here. But in this case, we've got a hypothetical rain event that wasn't that big, but it took it above ground level and caused a flood. Then the next ones were not quite so big. But the thing is that as groundwater comes up, it contributes, and then smaller events are now able to get over the threshold and get to ground level. And you notice then over time, the smaller rainfall events, some of them can be very small and get to ground level till eventually the groundwater comes out. Yeah. Now, in terms of what we think might be happening in the property prices and things is shown underneath here. As time goes on, the value of a house increases up to the time you get a flood event. Then it drops and discounts out by about 15%. That's the work that Quinn has done. As part of her PhD, and so it drops. But then in that case, in South Dunedin in 2015, it recovered over about 18 months. In fact, then, we got going again. The hypothesis is that over time, as the frequency of these events gets closer and closer and closer, then you don't get time for a full recovery. And so you drop a bit further and you drop it. It's like adding the groundwater as an antecedent thing. You've got an antecedent condition in the finance. And so you get to a point where you fall below where the banks are actually comfortable of giving a mortgage, or the insurance company are comfortable of insuring. And so you can end up with it falling below the bank zone, and then only cash buyers can buy a house. And so then you start to affect the social structure because you've only got renters in there and you've got cash buyers who are absent. And then eventually you can get the sawtooth thing where it drops to zero value, where basically maybe you can't flush the toilets because the sewers have filled up and there's just not the capacity. So you get this house value written off and it goes to zero value, and that can happen well before the groundwater comes to the ground. So this is where you have a stranded asset and you lose value well before, and this is what we're currently looking for in these models that we've had for our national assessments. We've been looking at median groundwater, when does it come out and flood. We're going to have a hell of a lot of trouble well before those things come out, through the loss of storage to rainfall and the need to invest in the infrastructure. So it's not a great picture, but the very final thing I want to leave you with is that in the perfect world, we would take some model of sea level rise and groundwater, and we'd be able to define some value, black and white. It's hazard, you're in the zone, you're out of the zone, you've got to move, you don't have to move, you've got to engineer, you've got to spend this much. In reality, from the models and because of the variability in the groundwater, it's very grey through that zone. So we might have hazardous down the bottom and we might have hazardous from free, but we've got this kind of transitional thing that we really don't understand. And what that's doing is that these models are dominating the uncertainty during the first part of our next 40 years or 50 years. Eventually, the uncertainty associated with which climate trajectory we go on will start to kick in. And then whether we're on RCP 8.5 or 4.5, how we're tracking will be the important thing. But in the meantime, the uncertainty in the physical models dominates, either through which model do I choose, or through just the variability of groundwater, not knowing how permeable the ground is, and all those other things that we don't know. And it's really important because at the moment, all the companies through the TCFD, the financial disclosures and the rules for financial disclosure, ask for people to work out what their future climate risk is. And everyone's sitting there looking at the whole big trajectories way out here, 100 years hence. But actually the insurance companies don't care about that. They need to know about the next 10 years. And the finance companies need to know about the next 10 or 20 years at most. So actually it's the uncertainty in the physical models that's really important for us to get on top of. And that comes down to not only clever modelling and clever observations, but precise surveying. So that's where you guys come in, and I thank you very much for the use of your GPS equipment. And yeah, I think we'll leave it at that, hey? Thank you very much.
Yeah, we probably have questions for one or two questions.
Thanks, Simon. That was a fantastic presentation. Just touching on something you covered near at the end about impacts on the stormwater and the wastewater networks. Do you know if the DCC has picked this up and is starting to look at that impact?
Yeah, absolutely. So one of the things that after we got the groundwater monitoring in was we then set monitoring on the stormwater and wastewater system, trying to model the base flows at night when people don't flush the toilets, to see what the groundwater input might be, and then looking at what's the current flood model, and then they're putting in sea level rising groundwater models into the stormwater model, see at what point that actually starts to kick in and what sort of size of networks they're going to need. But yeah, no doubt about it. They know about it now. They didn't 5 years ago. Yeah. Don't know. Has anyone got anything online they wanted to ask? Is there a chat somewhere here, or can I stop sharing? Yeah, nothing there. No.
Simon, could you speak to a little bit to how you think having this kind of, really thorough scientific information out there is helping or hindering people in that live in South Dunedin, affected people?
There's no doubt about it. We tread a delicate line. So initially, in 2015, there were a lot of angry people. And Claire Curran, who was the MP, kind of together, there was a South Dunedin Action Group that kind of turned against the DCC, because at that time they were using the excuse of climate change. Mayor Cull at the time was saying, well, you're probably all doomed anyway, so climate change is going to get you. And they're all going, look, just clean up the stormwater system. And eventually DCC acknowledged that they had caused a problem. Then Claire Curran, as the MP, recognised that we've got a real problem because we've got the community still angry with the DCC. We've got to bring them together. So we used the diplomacy of science to say, well, hey, guys, we've got a problem here. It's not just them. It's not just them. This is the natural system. So she got me in to start working on this. And that's how I got involved, was creating a common enemy out of the climate situation and sea level rise and the rain rather than each other. So that then launched in the South Dunedin Community Network, got formed and so forth. But having that constant reinforcement of, groundwater is a real problem in South Dunedin is definitely causes a social effect, and people think about that, and they don't want their house values to be affected by it, no way. And they want to be there, they want to live there. So the whole South Dunedin Future program has been around how do we find the best way forward that we can improve things rather than, just fight and flight. The thing that really got me, that made me realise that we had won, was the day that headline came out and they interviewed the insurance companies. And the insurance companies are saying, yes, we know there's an issue here, and everyone's scared of insurance pulling out. And they haven't got around to really pricing on risk yet. But the insurance companies are saying, yes, we know there's a problem here, but we want to know that you're on top of it and understanding it. We're definitely pulling out if you don't. And we want to know the community and the council are together on it, and that something's being done coherently, or we're out of here. So to me, I think we're kind of winning, but there's always that delicate thing between highlighting the problem and sticking your head in the sand and kind of doing the ostrich thing and pretending it doesn't exist. So, some people are very angry. And in fact, we had a Meet the Scientist night one night, and, I just was completely floored by the anger of people who just said climate change is bullshit, rubbish. And they got, we had basically ended up kind of slightly scared leaving, at the end of the night. So, and that was just still, that denial factor is still there.
How long ago was that?
2 years ago. Yeah, yeah. Still, I mean, it was still fresh. Hmm. So, all right. Well, let's leave it there. We're 1 o'clock. Need to run.
Let's join the two. Thanks, Simon.
Thanks for coming, and thanks online. Do you want to press a stop on the record or something? Or? Sure.
Yeah.